Sometimes you have to make a judgment about boiling point based on structure. Although we haven't done organic chemistry, but if we give you a molecule, for example, cis-1,2-dichloroethene, and if I give you its structure, the way it looks like, now cis is when you have the two attachments that are different from hydrogen on both sides of the carbon, a double bond carbon. So in this case Cl, and I'm not going to put the lone pairs of electrons. And there is an isomer of that known as trans when chlorines are opposite to each other. So trans, like transatlantic across, cis one-sided. Which one should have higher boiling point? So the few things you can do is say carbon compared to chlorine, carbon is positive, slightly partially positive, and chlorine is negative. That we all agree upon. What happens if I put another molecule of cis next to it? How do they line up? And this is how they're going to line up. The hydrogen side is going to be on the side of chlorine due to polarity. Because remember now, this side is negative and these carbons are positive, and this polar compound is going to have that sort of intermolecular forces, so they are just going to sort of line up like this. Since it is polar in this direction, it will have higher boiling point, and it's actually 66 degrees Celsius. If you look at, for example, a case of trans, the carbon is slightly positive, chlorine is negative, positive, negative. What they do, they cancel each other out. So this is a non-polar sort of a molecule. You can have a dipole moment that cancel each other out. So this is non-polar, therefore lower boiling point, and boiling point for this is actually 48 degrees Celsius. Another molecule, if we give you the structure, there's two nitrophenol. So we give you the structure, you don't have to worry about nomenclature and how to draw it. But this is a benzene, you have a hydroxyl here and a nitrile here. So if we give you this versus something that is known as 4, so if I give you a 4, for example, is on one carbon you put hydroxyl, 1, 2, 3, 4th junction you put your nitrile, NO2. Now, which one has lower boiling point or which one has higher boiling point? If you look at the two, the hydrogen is going to make some sort of internal hydrogen bonding with the nitrogen next to it. So this is inside. This is known as intramolecular H bonding. And this will make this molecule to sort of stay internally, and it's just one unique molecule, therefore doesn't have much affinity exterior wise. So I'm going to say this should have lower boiling point. In a case of 4, if you line up another one next to it, what happens, they go from across each other, and the two molecules are going to form external hydrogen bonding, which is intermolecular. So they are going to have this affinity exterior wise, and this is intermolecular H bonding, and that causes to have a higher boiling point. And if I give you the numbers, the first one is 216 degrees Celsius, the later one is 279 degrees Celsius. Sometimes you will be challenged as which one is more volatile. The one with lower boiling point is also more volatile. Volatile is when the liquid turns into gas. So remember that many times they ask you on boiling point, but on a rare occasion they will challenge you which one is more volatile. Finally, there are a few things that I want to clarify. One is London dispersion forces. I keep using molar mass, but your new syllabus wants you to emphasize number of electrons instead of molar mass. Although there is a direct correlation between molar mass and number of electrons. For example, neon. Neon is lighter compared to krypton, both noble gases. Neon, the light one, has 10 electrons, krypton has 36. And you see the one with more electrons will have higher boiling point because the electrons are those that shift and create induced dipole moment. So remember this. The second one is surface area. If nothing else to argue, be able to just look at the distinction. Pentane, for example, is a molecule that has 5 carbons, and they go as a sort of a line. This is pentane. If you put another molecule of pentane next to it, they will line up next to each other, they pack well, and this has a humongous surface area because of this linear nature, and this is going to form lots of exterior bonding, intermolecular bonding. Therefore, this one has a high boiling point. But if you look at 2,2-dimethyl-propane, which is an isomer of pentane, that molecule looks like a spherical molecule. It looks like this: CH3, CH3, CH3. So it will have lesser surface area because now this is a unique molecule, and if I put another molecule next to it, they only have one contact place. So due to smaller surface area, this one will have lower boiling point. So the two molecules just have affinity here, so this will have lower boiling point because of a smaller surface area. So sometimes your argument should be in regard to surface area and its reduction of London dispersion forces. Finally, I want to look at water versus ice and sort of be able to justify why ice floats on water. If you look at water molecules, they form hydrogen bonding. So when you put a bent molecule H2O and another H2O in vicinity, they are going to form hydrogen bonding. So I'm going to put it in orange. And this is hydrogen bonding. But that hydrogen bonding is momentarily. They break, they freelance, they walk away. This gives lots of space between them. On the other hand, when you freeze it, when you go temperatures below 0 degrees Celsius, these hydrogen bondings are going to fix in place. And what happens is 6 molecules of water sort of get locked into a hexagon shape, and that reduces the volume, and therefore the density goes up, and that's why water molecules sort of floats as ice on water. So these are some final points I want you to remember.